Yo, what's up, everybody? Welcome back. Today we are adding defer to C using some ungodly macros, some things that should be criminal, never allowed. And so the idea here is sometimes in C you open a thing and then you want to close it at the end of the function, right? You might write some function like int main void, and in here you might do something like what is it, file star f is equal to f open thing, right? And like at the end of this function you want to call f close thing, right? So that the file handle doesn't just like fucking leak. What does this include? stdio or something? I haven't written C for a little bit. Right, you might do something like this. And if you were to early return if true return, then this f close would never happen. You'd leak the file handle. Uh-oh, no good, right? Oh, you need fucking like std bool for this to work. Like this. Yeah. Right? This f close never executes. Ruh-roh, no good. So what do we do? Well, a common pattern here is you might have like an out label here, and you might do like return ret, and then in here you would say like int ret equals 0, ret equals 0, go to out, or something like this, right? You might do something along these lines, and that way your early returns will still execute all your cleanup stuff, right? I was thinking it would be fun to not do that, right? It would be fun if you could write instead defer, maybe like f close f in here, right? And this thing executes at the end of the block. Then you don't have to do any of this, it just kind of happens. Wow, fun stuff, right? Now, obviously, this doesn't work, but I was thinking, there's like a thing that people do when they're writing exploits called return-oriented programming. So the idea here is, way back in the day, Clang has defer. That's not the point. This is funnier. This is a funnier answer to the problem. Obviously, if the compiler can do it, that's fine. So like way back in the day, you would find some exploit in some code that let you like write arbitrary stuff into memory. Right? Some buffer overflow lets you put some shit on the stack. Then you would like find some way to like trick the executable into like jumping to that point, right? Eventually, like 20 years ago, they discovered that this was bad. So they started doing this thing called write XOR execute, which says like, hey, maybe like the places where people can write to points in memory, maybe we shouldn't also allow them to execute those things, because like obviously like most people aren't trying to do that, and it's dangerous, so don't do that. And so we're like, oh no, how do I exploit people now? And then we have this like genius idea, wait a second, there's already a bunch of code, right? libc does like everything we could ever want it to do. We just have to figure out how to like make that thing happen, right? And so there's this thing called like return-oriented programming that says, hey, every function, there needs to be some like user input parameter to a function, which is like, where did I come from, right? Because you can't, if you're like in some function, my function, right? You eventually return to this thing, and you don't know where you're going until runtime, when somebody has like decided to call this function, right? Right? You can't, some functions can be known at compile time. If I just write like my func here, the compiler like can like inline that thing, and we don't have to go through that work. But like in some cases, if we have like if argc is equal to 2, right, my func, now all of a sudden we don't really know if this function is going to be called until runtime. So maybe this is like a bad example, but there are like some conditions you can create where you need user provided info to know where this return goes. And so what you can do is you can just abuse that. If you find a buffer overflow, you can say, hey, instead of returning to like where you actually came from, like return to like some arbitrary function, right? Because the return address is just sitting there in memory. It's just sitting there and you can like fuck it up, right? And so what people do is they like create these like gadgets, they call them, where they find like sections of code in libc where the end of the function does like useful thing for my hack, right? My hack. And like maybe before this, there's like, useless stuff, right? We don't care about this. We want this thing to happen. So somehow we like force the return thing to go here. And then we can like inject another fake return address. And then this will like go to some other function that does another useful thing for my hack, right? So hackers have this like way of basically stitching together pieces of code that are in an executable and calling them in arbitrary orders, and all you have to do is write a little bit of memory. And so my thought is can we abuse this same concept to make things happen at end of scope, right? Maybe we could write some macro that says basically like some ROP shit goes here, and when we get to the end of this function, instead of returning to wherever we called from, we return to this, and then this guy returns to where we actually called from. That's kind of the idea. I haven't really thought about it more than this. I just like had this thought yesterday while I was walking my dog, and I was like, no cheating, no looking, no further thought. We must do it on stream. And so that's kind of where we're at. So I've never really done this, but I suspect it's not that hard. So the plan of action is to start by just doing any ROP, right? Just like make sure that we understand how to overwrite the return address and get it to go somewhere else, right? Then we can try to like make a macro that like wraps that stuff, and then I assume that we'll find some like problems by making that macro. We can try to like iterate towards something more useful. Obviously, no one should ever do this. It's just kind of like a fun little experiment to run. So let's start simple. Let's make a function main, and in here, can we like just put like hello world? And I'm using puts here instead of printf because it's a simpler function. And if we just like compile this thing, and run that types hello world, which is huge for us. Can we look at the disassembly of this? Objump d test. Cool. So where's main here? Main is here. I guess what we actually want is we want another function, right? And we want him to do this thing, right? So that we can see how the stitching works. Something like this. We're going to be careful with compiler optimizations, right? Because we don't want to deal with that shit right now. But okay, so when main calls this guy, he just types call. Sick. So I don't know if this is function prologue stuff or like, I don't know if x86 is, or 64 is caller save or callee save. I don't really know if there's supposed to be like function prologues or not. But we can maybe assume, you might want -m intel. Yeah, you're right. Fuck AT&T syntax, am I right? Yeah, okay, I guess first let's look up the calling convention, right? That's kind of the play. So if we go to x86 calling convention, we look for the x64 part. Let's try to figure out like what is expected here. So they place arguments into a function in, this is Microsoft. Fuck Microsoft. Here we go. So we pass some arguments in registers, then floating point or integer are slightly different. Added arguments are passed on the stack, right? Integer return values up to 64 bits in size are stored in some register for output, and blah blah blah. What about like like stack management. Who's in charge of that? Um, I assume that like functions know. I mean, if things are passed on stack, then that means the caller is kind of in charge of making that space on the stack. So that's interesting. And so like I don't see anything in the assembly about like specific like uh how do you call this? Like return pointer manipulation? Right, he kind of just says return here and it kind of like knows what to do. Is kind of my feeling here. So I quickly Googled return instruction before this, just like in like the stream starting time. Sub RSP 0x8 is allocate space for the stuff we need. Ah, I see. So like here somewhere on where was main? Main calls our function. So he's creating stack space for our function. But he doesn't like inject the return address. You know what I mean? Unless unless call does that. Can we look at like x86 or x64 call instruction as well? What the fuck does this guy do? Okay, so I was seeing on the return instruction, they have like kind of like pseudocode for this. And they say like, there's like near returns, far returns, but we can kind of like assume we're doing near returns. We can assume that our operand size is maybe this. Maybe operand size is 64. We're 64 bits. That sounds kind of right. Then he says like if the top 8 bytes of the stack are within the stack limits, then we set the instruction pointer to the thing on the stack, right? So I think that it's likely that call also pushes that thing onto the stack, right? So he pushes the instruction pointer as part of call. Yes. Right? So it looks like here the function we say before the function starts, put 8 bytes, allocate 8 bytes for the stack. Then I'm not sure if push here allocates another 8 bytes. It might. But we have to assume that at the very least, the last thing on the stack is our return address. So we can probably prove that, right? If we compile this thing with debug symbols, and then we run this thing with that, we can put a breakpoint here at the entry to my function, and we can kind of take a look. Wow, I don't have GDB. That's crazy. That's crazy. Random, what's the paint icon and the one right next to it? One of those is my image editor, and one of those is color paint. Oh, 0 might save you. Also show you the saving of RSP by the callee. I think it does. Is it not O0 by default? If not, then we should be doing that for now. Oh, I guess not. Okay. Obj dump. So you're saying this might show us something a little bit more interesting. So here we have. Oh yeah, so this guy, he's got frame pointer stuff here. So at the beginning of a function, typically you have the stack pointer, which is like where do I put arguments, and then often you have the frame pointer too, which is where did this function start, which makes it easy to like reset to the beginning of the function somewhere. But yeah, we'll figure it out. Okay, let's GDB. Oopsies, GDB test, probably not test.c. And can we break at myfunc and run? And we should be able to like inspect our stack in some way. So we can like ask what our registers are, and one of these registers is surely the stack pointer, and stack probably grows down usually. So things that are our return address, we're expecting it to be up from this thing, right? So if we print this thing as a U64, uint 64t star, can we, how do you do this? Unsigned long. Okay. So here we're expecting this thing to be like -8, -16. Can we maybe disassemble? Where are we? Right, so my function, the first thing they did was they pushed the frame pointer to the stack. Then what is this AT&T syntax? So it's they pushed the frame pointer, then they set the stack pointer to the frame pointer, so it's left to right. Okay, so I guess what we actually want to do is we want to step by instruction until we get to the return. Right? Because this is where we're expecting to see our thing on the stack, right? So if we look at our registers again, and we look at the stack pointer, unsigned long of this. This is an address. Nice. So if we disassemble this guy, this should be main again, right? So this is 4B, which is here, right? So on return, the top thing on our stack is the address after the line that we called. So that's pretty good. You might want to use re2 here instead of GDB. Yeah, but I don't know that tool. So, it is what it is. Okay, so all we have to do is write some assembly that replaces the return address on the stack. And so we have to find that thing somehow. Now, we know that with O0, there are frame pointers. I think sometimes frame pointers are omitted, right? So I think it doesn't have to, but we'll assume for now that we have frame pointers, because I think that you can compile with gcc fno omit frame pointer or something. So we'll assume we have one, and that should make our lives easier, right? So going back to this guy, we run with GDB, we break on myfunc, we run, disassemble, we are here. So like we're at some arbitrary point in our function, right? After the stack has been set up. So can we look at the pointer to our BP now? Right, so we have the frame pointer, so we have the stack pointer and the frame pointer, which are pointing to the same place right now. How does like this work? What does pop do? What is I want like I just want this. Loads the value from the top of the stack to the location specified within the destination operand, or explicit opcode. So here at the end of this guy, he's popping the top value from the stack into the frame pointer. So here he pushes the frame pointer onto the stack. Then he sets the current frame pointer to the current stack pointer. Then at the end, he pops back into the frame pointer. So that means that here, for everything in our function, the frame pointer is pointing to our the stack at the start of the function. So it's like you have stack, just like memory stuff. When you enter a function, they have, in registers over here, they have like frame pointer, stack pointer. So stack pointer is like, where in the stack am I? When you push, they push the frame pointer into here, old FP, then they copy the stack pointer into here, and then stack pointer will like change as we like walk through the function. So frame pointer, and before all of this should be return address, if I understand correctly, right? Because at the end of the function, we pop this guy off, then we return, and so this thing has to be at the top of the stack there. I think that's how all this works. I think. So at like an arbitrary spot in the function, we should be able to look at the current frame pointer, which is RBP, unsigned long, and this hello, oh, unsigned long star, my bad. Now this is pointing to the old, this is pointing to the, hold on, this is pointing to the stack at this point, which has the old frame pointer. So we need to go -8 here, I think. No, +8? +8. Here we go. So we have the old, so at an arbitrary point in the function, the frame pointer is pointing to this guy, and we want this guy. We want to modify this. So we just modify old frame pointer +8, and we just point this to somewhere else. I think. So let's start by just trying to fuck some shit up. Okay. So int other func. And we should put never called here. Okay. And what are we expecting to happen here? We want to do some like bullshit here that forces us into this function, despite the fact that it's never called. Right? So I think that we probably want to do some inline assembly, right? Because I don't think we really have the ability to just like modify the stack pointer from normal C code. So I did Google inline assembly really quick. It's been a minute. So I think that when you do inline assembly, you have the assembly you want to write. So can we first just start by trying to get the stack pointer, right? That would be kind of nice. So you have output operands, input operands, and clobbered registers. Output operands, inputs, and clobbers, right? That's kind of what goes in each of these. So if we want to just get the stack pointer, we could say, we want to move the stack pointer, or maybe the frame pointer, into, fuck, I'm gonna get so confused by Intel and AT&T syntax, they're backwards. Can I force Intel syntax? I think that's how I got here. I think you can just be like, you can let GC use Intel syntax by adding it here. So do I just like slap this at the top of every time I do inline assembly? And then I think Intel syntax is, we can kind of copy from here. Intel. So they do stack pointer to frame pointer, right? So this makes more sense to me. Yep. So they were like, move into some register the frame pointer. So we just need to pick a register for this, right? Where is this going to go? And we can just say, we can pick any register we want. So let's do like EAX, right? And then we say that we have an output register here that is EAX. How does this work? I just need like an example. I need an example. So here they say, oh, interesting. So you define, you let it pick, right? You can do that. So you can say like yo, name this thing output, and can we do like inline ASM GCC? I just need some like quick docs here. Constraints maybe? No. Okay. Output operands, a comma separate list describing the C variables modified by instructions in the assembler template. An empty list is permitted. C output operands. Here we go. So what does the stuff in the string here mean? This is symbolic name constraint. Okay, so a constraint specifies blah blah blah. Output constraints must begin with either an equals, a variable overwriting an existing value, or plus when reading and writing. When doing equals, do not assume that the location contains the existing value on entry to the ASM, except when the output is tied to an input, right? Because the compiler might like do some crazy shit. So here we say we are clobbering this thing, and we want this to modify stack pointer or something, or frame pointer. Right, that's kind of the dream here. So here it's actually just no pointer. And then here we go like unsigned long frame pointer. Like this, I think. And does this have like commas here? No. Why is he mad then? Why is he mad then? This feels like it should be okay. Might want to try int3 first. Yeah, that's not super crazy, but fuck it, you know? And then can we like printf ul lu? Yeah, like this. Frame pointer. And I guess maybe we want like in hex, actually. LX? How do you do this language? Yeah, there we go. Okay, so he's mad because missing terminating. Oh, does it just be like this? It does. Junk at end of line. First, unrecognized characters M. Do I need like this shit? Operand type mismatch for mauve? RX, maybe? Oopsies. No such instruction. You need to finish with ASM ATT syntax? Really? Is it that fucking stupid? Not convinced. Oh, and then, oops, we're not supposed to use RX here. We're supposed to use output, like this. All right, I mean, I'll believe you. Okay, so that does seem to compile, which is good. And if we run test, we do see something relatively interesting there, right? We see this number, and if we breakpoint here, does that number match what we were expecting to see? So info registers. So our base pointer is 4480. 4480. Okay, so this is good. This is good. We have the ability to run assembly and we can extract the base pointer. Okay, so what do we do with this? Right? We want to like fuck up the return address in some way. So if we were to say, let me think. Actually, yeah, we want to fuck up the return address so that it goes here. But how do we make sure that when after it goes here, that it goes back to main? Right? So I guess we just push a thing onto the stack. Yeah, we can set a new frame pointer here and a new. Yeah, hold on, let me think. So we need to, if we just overwrote the return address, it would never get back to main. So it's almost like we need to inject a new return address. Now that's gonna fuck everything. We can't just like change the frame pointer probably because the assembly is probably going to need to uh like the we might be referencing the frame pointer to like access variables on the stack. So I don't think we can just like change it. This needs to be at the end of the function before return. Yeah. So if you just return to the end of the function, then the default code will return to main for you. Yeah, but I'm trying to see if there's a way to like, my initial thought here was that we like, oh, I guess if we have full control over this function as well, which we will, then this guy can put the return back. Yeah. Hold on. Uh, I guess also since this guy returns 0, he'll exit the program. Okay, so if we put like return 1 here, we can say we can set inputs to this thing as well, right? There's inputs and outputs in the clobber list. Input operands, yeah. So how does that work? Input operands. Constraint may not begin with equals or plus. Okay. See constraints for ASM operands. Ah, here we go. So this is what a register operand is allowed. I see. So these are what the letters are for. Memory operand. I see. So here we're saying like, give me a register. So we can say, hey, I have this thing. And then I also have a register. And this thing is going to come from something. So does the input operands, do we put it in the square brackets? Or I guess it's like square brackets is name again. So this is the like new return. Okay. And we get this thing from somewhere, probably, right? So we can say like address of other func or something like this. And here we can say, instead of moving the base pointer into the output, we actually are going to have no output anymore. And we're going to say, can you put at RBP plus 8? I don't know if this is allowed. New return. Is this a thing that we're allowed to do? We'll see. I assume not. Invalid use of register, yeah. Move, you put square brackets around it. Okay. Oh, let's go, baby. So now we've managed to like force this thing to this function, right? So here, what should happen is we should see hello world. We enter this block. We go here. This print of the frame pointer never happens, which is, interesting. This is still happening, which probably means that like this is getting reordered. Can we look at the disassembly here? Obj dump. So in our function, my func, where is my func? Here. So printf is happening here. Oh, wait, because this isn't happening until the return. Of course. So we're modifying where this will go. When did we return 0? We end up here. And then never call is called. Yes, okay. And then we segfault because what? So I would have thought that at this point, I guess like we need to restore the stack in the same way main would. Okay, cool. So I guess the goal now is to like jump to some code that we inject within this function so we have full control of the stack. The return address of the second function is incorrect. This should go back to start, right? Because main, when he returns to start. So I was kind of assuming that other func would return to start. But like the stack pointer, the stack is probably all out of whack at this point. So probably if we might be able to like manually construct an assembly function that does what we want. But maybe we jump a little bit ahead here. Let's try to like inject some code directly into this function. So like ROP to myself. That's kind of what I want to do. You're not pushing the return address, so it's whatever lives above your current stack. Yeah, I understand. I agree. Probably the hello world string. No, wait, am I crazy? So this return 0 should clean up whatever was in this function, right? But the stack, the like pre-allocated stack from main before he called this function is not cleaned up. No? Yes. Yeah. What do you mean? Because all we're doing is we're changing the return address, right? So like, here, we can like look at this disassembly, right? Like this function, at the end of this guy, he sets the old frame pointer back and then returns pops the return address off the stack, and then main would typically after that like clean up his own stack. You changed the return address. You didn't write the one you overwrote. I don't understand what you're saying. Yeah, I did change the return address. Yes. I changed the return address to go to other function, so we end up here instead of here. At this point, like my stack should be whatever this guy was when he entered, like whatever it should be here in main. You moved. You didn't append. I know. What are you? Yeah. So like this, the stack should look exactly like it would here, right? So you need to return for the deferred call too. Yeah. So what I'm saying is like when this other function should like, if you skipped all of this prologue, you should have 3 returns. Well, I mean, like depending on what you want, right? I'm saying right now, other func is behaving as main, but then he's got like some like prologue shit. The code is going to return 3 times. You only have 2. I agree. F-omit frame pointer will fuck this shit up, though. I agree. I understand. Yeah, so like by going back to here, we're never going to go back to main. I understand that, right? Because like, but main was called by start. So I would have maybe assumed that other func should return directly to start in this chain, but we're probably seg faulting because the function prologue for other function is happening, which like fucks up a bunch of stuff. If we manage to skip the function prologue here, then I think we would probably be okay. In fact, we can probably test that, right? We know that other function, if we move to other function, plus some shit, we should be able to get to like his return. Like I bet you if we ended up kind of like here or something, it'd be okay. But anyways, it doesn't really matter actually. Let's just force it so that we have like some space in our own function that we can control and go there. Right? So I think that you have like, first let's double check. Can I like put an address to something? Like can I get like an address to code? Like can I go like if 0 never called okay, so we go here, we say this is never called, get rid of other function here, and can we go to label like this? I think in GCC there's an extension with double ampersand or something. Okay. Close. So this guy is calling hello world over and over again, which isn't good. I was hoping that he would go here. Maybe it's label +8 plus something. Maybe label goes after. So we're definitely doing something. It's just not what I want. Can we printf, you know, the address of label? Like, what is this thing? He wants %p. Sure. Okay. So, and we like, I guess, disassemble this thing. So we're looking for 113A. 113A. 36 3A. Ah, interesting. Wait, this should be fine. I guess maybe our stack is different. Yeah, so I guess the pointer of like what we're putting in the stack, or what the pointer to the thing that we're putting into the puts call is broken, but we probably are actually still ending up there. You could probably jump to the original return address. Yeah, true, huh? So if we have like, ooh, that's a good idea. So we could like make an assembly block here that extracts the original return, right? Okay, this is interesting because this is going to end up in like ret addy, right? But ret adder lives on the stack if we put it here, right? Which means that if we jump to that place, we'll be jumping to like a place that the stack like later may have modified. So it's almost like for now, if we put unsigned long here, ret adder and global space, then this guy can put that thing there. So it's output is RBP +8, right? Then here we should be able to inline some assembly to jump to that place. X64 jump. So we can jump relative. Is there like absolute? Jump far. So we can just throw a jump to a pointer. So you have indirect jumps to this guy. Okay. So can we look at like, is there a jump in this thing anywhere? So can we just like, oopsies, jump to, can we just like throw a new return in here and see what happens? Yeah. So here we start with move the current return address into this guy. Then we have an if 0 for to put some code that never happens in with a label. We put that label into the new return address and return, which should jump us to this place. And then here we just jump to the old return. That's kind of like the idea here. There's no jump to 64 immediate, but you always have to move register, add or jump register. Yeah, probably right. It's like, I assume that like this won't compile. It does compile, which is interesting. But then this isn't happening. What the fuck? And also, puts never called is interesting as well. Because I guess this never called might be using stuff on the stack. I would like to put a breakpoint here and just kind of like look at what GDB is saying happens here. Hold on. Hold on. Is it possible that this if 0 is getting like completely compiled out? Okay, obj dump. Let's look at this thing. So in my func, we have one call to puts, one call to printf. Is that true? One call to puts, one to printf. So that is right. Okay. Oh, fuck. GCC, GDB, break here. Okay. So I want to know, when we end up at our return, where do we go? Right, so here we're at the very end of the function at this return. Can we end up at hello world puts. Oh, wait, hold on. There's a, I'm a dumbass. So this thing might be like fully compiling out our puts. It might be, because it's if 0, which like it might know it doesn't need to do, right? There's no call to puts in here anymore. So what we need to do is we need to force this thing into the executable, right? So we could do something like this. Hello, if hello, I guess int here. Then we go into this thing and we trick the compiler into being confused about this thing, right? So we say, don't do anything, but like pretend that you're outputting some stuff into hello. Or something, right? You're clobbering this shit. And that should make it so that he doesn't know that this doesn't happen anymore. And he can't just get rid of that shit. Right, so now our call to puts is still there. Isn't this why the volatile keywords exists? I thought the volatile was, yeah, I thought volatile was like you... Oh, yeah, you have to assume that somebody else is writing to this thing. That does sound kind of true. Volatile C. What does it mean again? This, every access has to happen, right? Because, like, maybe this thing, is modified by, like, external memory. But I guess, like, this is kind of a little different, because maybe this could still be in a register, where I think volatile means it has to get a pointer. Might be a hardware register. Yeah. Whatever, this is fine. Okay, so now when I run this thing, we are getting to never called, which is huge. I do not like that we're not jumping, like, we're kind of, like, ripping this over and over again. Does this have to be plus some offset? Like, why is this jump? Where is this jump going is confusing to me. So can we GDB and maybe breakpoint at this never called thing? The fact that we're seeing that print at all is like a very good sign, right? So what's supposed to be happening here is we call this thing and then we jump to the value stored in RAX. So here we are at the call to puts. Now we are at this thing. Okay, and we're loading this address into RAX, I think. Info registers. So RAX should have this value in him. Oopsies. What the fuck just happened? Hello? Oh my god, what is happening? Stop it. So RAX has this, which I believe should be where we're trying to go. Disassemble this guy. It is just going right back here, huh? But why? Yeah, why is that happening? Because, oh. This is supposed to be ret adder here. Whoopies. Okay, so that's a better sign. Okay. So now we want to go to here. So now we are at this jump to RAX. Does RAX seem reasonable? So we are at B6, which is the thing right after the call to myfunc, which is good. That seems good to me. So then why are we segfaulting? So now we end up at return 0, hype. But we are segfaulting, I guess because maybe we didn't like restore our frame pointer correctly. Yeah, it could be that like in here, we have to do some restoring before we jump. But it's okay because we're kind of expecting to do some like more ROP chainy shit here anyways. Okay. Okay, so this is something. This is something. Right? We've managed to like inject something here. We've managed to get to this never called. And I guess what I need to understand is what are we missing here? I mean, ideally here, we could write return 0 here, right? And it just kind of like happens for free, which means that we kind of need to like treat the stuff in this block like a new function. Right? Like, it would be kind of nice if we could kind of just say, like, treat this like a new function call that returns the same stuff that myfunc would have returned. There's something there. There's something there. Because then we don't have to do this, like, hacky jump. So the question is how do we do that? Like, so when we call return here, this thing has at the top of the stack a pointer to where we want to go. On return, the return function or the return like assembly instruction will like pop that thing off the stack and go there. So we need to like inject that thing back. Right? Which I think that we could like make a naked function that allows us to like control exactly what's going on there. So let's, yeah. There's like naked function GCC. Or we could like just like inject our own shit. I guess let's try to do it inline first. So here if we just said like, so we have the return address. For now, we could just call push. Right? So like we could just be like push the new return address and then return. Or the return, yeah. We push the, I guess this is kind of like old return is a better name for this, right? Uh, okay, so that's a good sign. So here if we say printf, hi mom, we're back to main. That's a really good sign. That's a really good sign, right? So here what we've done is we come into this function, we inject some code that we don't call, we force ourselves to go there on exit. When we get there, we put the old return back into the top of the stack and then call return, and then we end up back here. That's pretty good. Now, we're definitely missing some stuff though, where we need to like preserve the old return value, presumably. We need to probably make sure that like the stuff that we're using here is okay, right? If we printf, you know, a variable here, x, right? X is this. Like, that's gonna kind of like depend on what the compiler does with x here, right? So if we put like int x equals 0 here, at the end of this, we put like x equals 5, and then we like run this shit, right? Like, we still see x is 0 here, right? Which is not good, right? Because we modified x down below. So how do we like force this thing to get like a pointer that we can use? And how, like, I guess also, yeah, it's like we have to like capture that thing, right? Because when we return, we've kind of like nuked our own stack and our own registers, right? Like as Null was saying, X could be in a register right now. So at this point, this could be like this what might be happening here is that we like take a register, put it on the stack, or like I guess like we just take the register as like the first argument to printf, and we just like we just call, right? And since x is already in the register at the beginning of this if, he assumes that that is still the case here. So when we jump back, the registers might be different, and that's like not really fair, right? Right. If we look at the calling convention, the arguments are passed in RDI, RSI, RDX, right? So printf is probably just printing whatever is an RDI at this point, right? So if we run GDB here again and breakpoint here and hit run, info registers, we're probably saying RDI is RDI is 1, interestingly. He's putting Rex in RDI though. So before calling, so we could probably, if we said that this guy returns 2, I bet you we see that this guy prints 2. No, still no. Interesting. Interesting. I would have thought that that would do it. So can we look again? Can we look again? So where is this like call to printf here? Oh, is it the other way around? Is he moving RDI to RAX and he's... Oh, is this the wrong one? Hold on. I need to look at it from GDB. Okay. So we are here. And so when we get to printf, can we just make sure at the very least that I understand that the thing in RDI so we're at this call, info registers. RDI is this. So maybe I don't understand printf. Maybe RDI is param 1. But is printf not taking the first argument and printing it? Right? If we right, we are here. So int x here should be the first argument. Will this be on YouTube? Yeah, this one will. Doesn't this use varargs though? Oh yeah, which might be fucking X is the second arg? Oh yeah, of course. My dumbass. You're right. I'm sorry. You're right. Because the string is the first argument. So RSI is the second one. You're right. Which means that we're like info registers. So RSI here is 0. And so if we say, can I like set registers in GDB? Yeah, you can do set RSI equals 4. And then he says X is 4. You're right. My bad. Okay. But either way, the expectation at this point then is that when we get to this point, like the registers are set up as they were at the time, right? Right, so if we look at this thing, probably like this X value like just happened to be in RSI at that point already, right? Or here. It was in EAX or something, right? Whatever. So we need to like somehow capture the state of the stuff that we want to use in here at that time, right? Which is confusing. So it's almost like here. Can we like modify the stack somehow? Right, so it's like here if we did something like push stuff to stack. That we want to use in defer. Then we would need to jump to a point that restores that stack somehow. Which is not very trivial. Right? Because all we're doing, like the goal of this thing was to have this thing automatically happen on return. And so the only thing that we can do is jump to somewhere else. I guess, can we like, we could have like an external stack. That's not that crazy, right? So like we don't know what the compiler is going to do to like the stack at this function, but if I just had like this like defer stack over here, okay, hear me out. Void star defer stack. LG, thank you for the tier 1. And Holigus, thank you for the prime. Much appreciated. Yeah, so I have like a pointer to this guy. And in here I have like defer, like uint64t defer stack, you know, just like something like this. And I manipulate this external stack pointer to hold the stuff that I want to track independent of the function. And then I can put stuff there and in here pop it back off. This is awfully close to a coroutine. Yeah, it is awfully close, huh? So can I just like set the stack pointer to this thing, do whatever I want, then set it back? That sounds like possible. Okay. So Okay, hold on. My brain's like hurting a little bit. So what do we have to do that is the other question, right? Um and you know what? It's almost like we want to force all of this stuff to get like, so if we need stuff to get like stored somewhere, then it's almost like this should actually be a function. Right? Like we could have like uh int void do cleanup or something. I don't know yet. And like this guy should take in x as x. And do we not have like inline functions in this language? Or not inline, like nested functions? Oh, you need to wait, no, that seems like it's fine. Double square double z return z times z. So why doesn't he like this? Oh, maybe it's Clang doesn't like it, which is fair. Which is fair. So like the language server doesn't like it, but GCC is okay with it. Okay. So if we do this, then we can like restore things from our stack somehow. Like we kind of know the argument order here, like theoretically. Like it's almost like we want to put so if we want to see changes to x that happen down here, it means that we have to force x to be taken as a pointer, I think, so that the compiler knows that we might use it here. Then we need to somehow like restore that pointer here. Yeah. Yeah. That's kind of close to what we want. Now, can I what's like the like naked function GCC thing? Like if I want to prevent my function like I want to like completely manage stack and stuff, what does like naked do for me? Does it still I assume that it still has to follow calling conventions? I assume. So oh, can I not um yeah, that's fair. Okay. So maybe it's unsafe to do this. Maybe. But it is nice, like syntactically, to have, you know, a scope like this that is forcing us to only use variables that like we're allowed to use. You know what I mean? But yeah, I guess maybe in a naked function, GCC doesn't know what to do with those things. So because it was safe until now, yeah, yeah. Uh, so like maybe we just say, okay, you can use any variable you want, but then how do we, like we still need to like manage intentionally like keeping track of stuff. So let's go back to the idea of push stuff to the stack that we want to use and defer. And by to stack, I mean our stack. So let's pretend for now that we have like define like push item. And this is going to turn into like the name, you know, item. And this is like just an ASM block who calls you know, he has like inputs of This is outputs, then inputs. He has the input of stack pointer, right? Which comes from, in a register as defer stack pointer, right? And he also has the input of the element that we want to push, right? So it's kind of like this. Maybe the address of that item. Okay. That's not crazy. Then we can say that, like, we move this item onto stack. So can we, like, get this, like, Intel syntax shit back in? Yeah. Okay. So here we move into stack pointer item. And then we increment the stack pointer. X64. We could do a stack pivot, true. But I don't know how to do that, so. So this add goes to a register. Can we, like, x64 add to, yeah, you probably do, like, yeah, you probably, like, say, like, an output as well. Add. Yeah, so you add to a register, I guess. So we add stack pointer 8. And then we store that, right? So stack pointer is a clobbered thing that we want to be tied to defer stack pointer. So then it's like move. So it's like move into the stack pointer. I think it's like this, actually. So we, like, we might modify this thing. We come in as stack pointer. We have the item as an input. We move this item into the thing pointed to by stack pointer, and then we add 8 to the stack pointer. I think it's that simple. So then we can be like, push item here, X, right? And now X is, we have a pointer to X sitting there on the stack. But I guess we don't have a guarantee that, like, X will stay on the stack when we get here. But we can hope. So then we have pop item. We kind of have, like, a similar thing, right? So here we, like, pop item X. Okay. And I guess we just start, like, clobbering stack. That's pretty funny. So, like, this function, the stack pointer has been, like, restored, but that doesn't mean, like, the memory that stack used is gone. I guess, right? So here we have an output of item. Output of item. And an input output of stack pointer. Yeah. Something like this. And here we move the thing at stack pointer into item. Yeah. And then we sub 8 from stack pointer. That seems like kind of reasonable. I'm not sure actually if this is going to move the thing pointed to by stack pointer. We might have to do like this plus 0 or something to like force it to do an indirect. Type mismatch for move. Okay. Yeah, so I worry about like, can we do this? Real quick. Fuck pop item for a second. Let's just look at push item. So that worked. And can we look at what that did? Hard to read, but let's hope. I think we might have to go back by 8 since the stack pointer's in the wrong spot. Or we do the sub first, and then we can do this. Where we like pull the thing back off the stack pointer after we've subtracted. I think that's maybe right. Okay, so let's pop item X here. And then can we printf X equals this? And then we push the old return and return. All right, let's see. No good. No good. But let's maybe take a look here and see what the fuck we've done. GDB, this thing, breakpoint here, run. Okay. So what's happening at push item here? So can we px here, p and x? So x is this guy, right? So set 4470. So this is in the stack pointer. Is kind of like the only thing that he's got right there. What is this guy trying to do? I was set disassembly for intel in GDB. Yeah, that makes sense. Disassembly flavor intel. This will help us kind of interpret in the same space. So okay, where's like, what did we call our thing? Defer stack? Yeah. Okay, so this guy's pointing to defer stack is at 404060, right? So that's information to keep in our head. So somewhere we're expecting to see an add to that guy. So I assume 404010 is, yeah, okay. So the defer stack pointer is at this address, 404010. The defer stack starts here. So this defer stack, we put the defer stack into racks. I don't know what this means. Move racks. Oh, I see. We like, this is dereferencing the thing in racks. Right. Right. So we load this guy in here. He's pointing to here. So at this point here, racks should be pointing to the defer stack. So racks here should be 60, right? Which lines up. Like where p defer stack is 60, right? So that's the thing that's in here right now. Now we move the thing in RDX into where we're pointing. So we like load from our frame pointer offset by some amount RDX hype. Right, so this is putting X is on the stack at this location. We put this in here. We put that on our stack. So we have a pointer to X here. Then we increment our thing. Then we jump over all of our shit, right? So what we're hoping to see here is, where were we? We were here. So we were hoping to see right now the value in RDX should be a pointer to X. So RDX is this, 4470. And if we print X, 4470. Okay, so that's really good. There we go. So that's hype. So then when we get to here, when we jump to our like bullshit, we should be able to pull that back off. Right, that's what we're kind of hoping here. So can we breakpoint? I assume it's here. Is like, actually, can we just do a list here and break at 47? Okay. So now we're trying to pop this thing back off. We're hoping that we look at the defer stack, and the first thing in here should be our pointer to X, 4470. Now can we, I'm curious if we set X to 5, right? So can we print this thing? 0 is not promising here, right? This means that like our write to X did not result in an actual change to the thing, right? We got all the way through here. X was written, but he didn't actually write to the stack. So out of curiosity, if we put volatile on this thing to force him to actually fucking write there, does that change behavior at all? Fuck. So breakpoint here, run. So we have defer stack here. Can we look at this guy? No. So that's interesting. Can we look at what this X equals 5 is doing? Whoa. Wait. Is this not happening? Is this just like straight compiled out? Hold on. Let's see, it's GDB, break here, run. Yeah, what the fuck? That's not behaving the way I thought it should. X equals 5 is me, see if your optimizations have optimizations off. Yeah, I understand that, but I don't. So I would have expected this to work. I would have expected. Okay, let's GDB, break my func, run, disassemble. Or maybe like list. Can we just hit like next a few times? So we go through all this. We go through if hello. Whoa. Wait a second. Is this not, why is this if hello not 0? Whoa. I guess this needs to be read write maybe? Because he might be assuming that he doesn't have to initialize this thing if he's not read in this ASM block. Could be. Oh, did we not compile? There we go. Okay, there we go. So now that changes a lot of the things that I was thinking about. So now we go return 2. He hits next. We go to pop item X here. And now we can look at the defer stack again. And we want to know, is this thing 5? Good. Very good. So we see our right to x here. We call printf. Bad news bears, he's not what I think he should be. So what up with that? What up with that? This thing said 4470. This says when I print the address of x, it's 4480. That seems bad. Right? That seems not good. So is that like because we fucked up the frame pointer and shit, and so it doesn't really understand where these things live, right? Maybe it thinks that like x is at some specific address relative to the frame pointer, which is no longer where it used to be. Right? Because the frame pointer has been restored by the time we return. Maybe. Okay, so let's take a look here then. Okay, so print x. He's at this address, right? If we look at the defer stack, he matches at this point, right? Then we run through all this shit. We get through our return. We jump over back to this place. And if we print and x again, the address has changed, right? So presumably this is because the way that the address of x is calculated is relative to the frame pointer. So we could hack this, right? So if we say set RBP is equal to, wait, can we like info registers for a second? So we have RBP at this guy. So can we say like set RBP equals this minus hex 10 and print the address of x again? Yeah. Yeah, so now we can see that the address changes, which is kind of interesting. And now, if we hit next here, ooh, still no. Okay, so this is at least the addresses right now, but now when we continue, we're gonna like crash or something. I'm surprised that nothing bad happened there. So we've got like a lot of work to do here. We have to restore frame pointer. We have to pop item. And pop item is not doing what we expect. So let's start there. So we're saying, hey, item is x here. We're saying, hey, put x in a register. Take the thing off the stack pointer. I actually think it's like this. It's like a double dereference, which is pretty funny because the stack pointer is pointing to the address of x. And if we're trying to load x with the address of x, we have to double deref. Which I assume GCC won't actually like here. He's actually okay with it. Stack smashing detected. Okay. Hold on. GDB this stuff? Okay, hold on. So at pop item x, we needed to fuck up the frame pointer, right? Because the address of x is wrong. We expect this to end with 7.0. So we say set RBP is equal to this. There we go. Okay, so now we hope, so we look at the first stack. And we're hoping that if we dereference this, we see 5. That's good. Okay? So now we're looking for the place where we load the value that we saw in there. So here, fuck. What was it? Set disassemble Intel disassembly GDB. I forget. Disassembly flavor Intel. Okay, so here we load, this is the pointer to our fake stack. We dereference that, we sub 8. Then we move into EDX, a dereference of that thing. So we're kind of hoping that here, EDX is 5, I think. Right, so here we have moved the thing in the point that RX is pointing to. So print info registers. We have Rex is the top of the stack. Okay, so that means that EDX is the pointer. Yeah, so EDX here is, we see that 4470, the bottom bits, the bottom half of the pointer here, that X is pointing to. So it didn't double dereference like I wanted it to, is what this is indicating. We are taking, unless I was supposed to do another dereference. Like, I'm assuming that, like, this seems crazy. I'm kind of surprised that that works, to be honest. It could just be that, that, like, it's just, like, a syntax thing, and it's not actually doing anything. Yeah, that's kind of how I'm starting to think. Yeah. Yeah. Okay. So what we actually probably want to do is, like, take the thing in the stack pointer, say that we clobber scratch. You know, something like this. Then we can, like, put that thing into scratch. And then dereference scratch into item. That's how I'm starting to feel like this should go. Now I'm concerned here because scratch here is like a register allocated by, like, the function, and, like, who's to say if that's okay in this world, but how does, like, clobbers work? Oh, I guess maybe it's like, actually this is like this. Maybe clobbers is for something else. No. Yeah, he's expecting, okay, let's read again. Clobbers, clobbers, clobbers. Inline assembly. Do I have this open anywhere? I guess not. Oh, maybe it's here? Yeah, this one. This one. Okay, clobbers. Oh, so we just, like, manually write one here. I see. We don't, like, allocate one. So we could just say, clobbers, like, Rex or something, and then we can use Rex instead of scratch. I think you don't need plus zeros on these, by the way. Oh! Oh! Look at this! X equals 5! We got there, baby! Okay, so we also need to like unfuck up our frame pointer kind of automatically. So like restore frame pointer, which is gonna be some like fucking inline assembly that like moves. Let's just do like, we know right now it's add, maybe it's subtract 10 to RBP. I can't remember. It was like something like this. Something like this. So let's just slap that here so that we should get rid of that stack smashing stuff. Still not doing what I want. Maybe it was sub. Oh, it's hex 10 as well. Oopsies. Let's go! Let's fucking go! So this is fucked. This is like absolutely fucked. So if we take the volatile off x here, like, does this x equals 5 still do what I want it to do? I think there's like a good chance it doesn't. It still says x equals 5 there. That's good news. Because I guess, like, here we're kind of saying, we're telling the compiler, like, hey, we're, like, putting that address of x somewhere, and you don't know what's going to happen to it, so, like, you can't touch it, is, like, maybe what it's learning. Then like, we go through all this, we set x equal to 5, we return. From this return, we end up at label, and in here, we say, okay, they already just fucked up the frame pointer, so, like, really, we should push the frame pointer as well, as, like, a thing that, like, that's maybe like, the first thing that we do. Except we don't know, like, as we push to our stack, we kind of need, like, the old frame pointer to be the last thing there, right? I guess, right? So we, like, maybe we have, like, push frame pointer here, right? Who basically does the same thing as push item, except he's moving, instead of from item, he's not pulling anything in. It's just like RBP here. Yeah. Then popping that thing off, we can pop the frame pointer off instead of doing this, which is the same as pop item, just the hard-coded frame pointer. So everything says item here. Get fucked. And here we say substate from the stack pointer and move into RBP the thing that was in the frame pointer at that point. Yes. So now we should be able to, push frame pointer and restore frame pointer here. And that should still work. Nice. Nice! And so now the question is like, how fucked is this? Like, can we actually turn this into a macro of some form? Like, maybe. You could maybe write, like, a variadic macro that said, like, here's my capture list. I don't know how to do, like, variadic macros here, but you could have, like, you could imagine something where we go defer, X, Y, Z with this shit in it, right? And then in here, we can go, like, printf X is equal to X or something, right? You could imagine this maybe working. And you would just have to, like, punch in a bunch of, like, names here. You would have to, like, do all of this shit, right? So you'd have to iterate over the arguments and push each item. Then you would have to push the frame pointer. Then have some sort of, like, inline boolean here with a special name that is, like, forced to be compiled in. Then we check that thing, restore all of our shit, and then return. And then even here, this is probably still not right because at this point, like we need to restore the frame pointer to where it's supposed to be. So like really here, it should be like put RBP on stack, on like actual stack. And then at the end of this, it's like pop RBP off actual stack, right? Which is fucked. And even then, I'm not really sure this works. Because again, like there's so much stuff that could go wrong here with anything in scope at this point. Like, who's to say that it is actually still in scope here? Or sorry, at the end of the function where it was like where we're actually using it. So we could push this idea farther, but I think it's fucked. Obviously, it's a bad idea, but I think it's an even worse idea than I originally thought. I mean, we got something that like does what I originally was thinking of. It's just that like the idea of this is so much worse than I originally considered because of the fact that like you don't know, it's hard to predict what the compiler is going to do after this if statement. So even though you can inject whatever the fuck you want here and do whatever the fuck you want, it's like it's just hard. It's the information that you need, I think, is like not guaranteed by the compiler. You could maybe get even crazier and have like, you know, defer available var. You know, you could like annotate this thing with a thing that makes it volatile, but that's getting like hairier than I would have really wanted. So I think that we can say this is as far as I want to take it. Which was still fun. This is fucked. But funny. So, yeah, I think we call the experiment finished here. Thanks for watching, guys. If you like what you saw, we stream most days. We aim to start at 12:30 Pacific time and stream for like 2 to 4 hours. It is 2:30 Pacific time now, so if you're watching live, 2 hours ago till like an hour and a half from now is usually when you expect to see us. You know, this is like kind of like a one-off stream. We're actually working long-term on like a neural network training thing to scan barcodes for us because we're too stupid to figure out how to do like proper image processing ourselves. So if you want to see that, swing back by in probably 2 days from now. I'll probably skip tomorrow. There's a YouTube link in the description where like, you know, a lot of stuff goes up. Some stuff does not. I might stop posting the barcode stuff there because YouTube really doesn't care about it. And maybe like start posting again when we get to like actual neural network training. Not sure. But if you want to access the stuff that I don't post there, you know, that is the rest of the VODs go up on Patreon, YouTube members, or in Twitch VODs. And if you subscribe in the appropriate place, you get knowledge that you are helping the stream survive. Because, you know, I will get a job when I run out of money. And you get access to the VODs that I don't post on, you know, main YouTube. The YouTube algorithm is fickle, right? So things that are interesting are not necessarily the same set of things that will keep the channel alive on YouTube. So we have to be a little bit conscious of that. But anyways, that's it. YouTube, peace out, and Twitch, let's find someone to raid.